Your grandma just died and left you an inheritance of 25 grand. You are 25 years old and wish to invest all the money for your retirement. Your broker gets you a deal at 8.25% compounded quarterly. How much money are you going to have in your account at age 65? So your formula for compound interest. So the amount of money that you're going to pull out of the bank depends on your deposit, your original deposit, the principal, times 1 plus the rate over n, which is how many times you're going to compound it, how many times the bank's going to pay you interest a year. And you're going to raise that to an exponent of n times t. And t is how many years you leave that money in the bank. So the first problem, you got to figure out all these numbers, what we're going to put in. Okay, the dollar sign, that's what we're trying to figure out, how much money we're going to have at 65. P, that's our initial deposit, so that is 25,000 times 1 plus, okay, your rate, you got to change it to a decimal, so move it 1, 2 times to the left, so it's going to be 0.0825 over n. N is how many times it compounds. It compounds 4 times a year. And then raise it to the n times t. So 4 times t is in years. How many years you're going to leave that in the bank. So if you deposit at 25, pull it out at 65, we're going to go 40 years. Let's say that money sits there for 40 years. Okay, now this is ready for a calculator. So just plug it in, hit enter. 25,000 times 1 plus 0.0825 divided by 4. All raised to the 4 times 40. So at 65, you should have available 6 I think I did something wrong. I think you should have almost 750,000. 655 grand. 439.0941. Okay, so you asked your broker if he can do any better. And he tells you that if you increase the principal by another 5 grand, he can get you the same rate but compounded continuously. So the bank will pay you interest all the time, every second of every day. How much will you have at age 65 if you choose this route? So you've got to increase your deposit by 5 grand. So the money you're going to have at 65, now this is a totally different formula. If you're getting paid interest continuously, that's the idea of E. That's when E shows up. So the formula is the principal times E. This formula is kind of a little bit simpler. And then R times T. So that's it. So it's quite a bit easier actually. So the money you're going to have is 65 equals what you deposit. So instead of depositing 25 grand, you have to give your broker 30 grand. And you're going to times that by E. Your interest rate stays the same, so it's 0.0825, and you're going to leave it in there for the same amount of time, 40 years. So punch this in, 30 grand times E to the 0.0825 times 40. Okay, you will have 800 grand. 813,379.1676. So that's how much money you'll have at 65. So not bad. Turn 30 grand into 800 grand. Okay, but you're actually hoping to retire with $1 million in savings. So how long are you going to have to leave that money in the bank with option 1? So option 1, you're only going to pull out 655 grand. And your goal is to retire with $1 million. So the question is, how long are you going to have to leave that money in the bank? You're going to have to leave it in longer than 40 years. So now we're going to take $1 million. 1 million is what we're aiming for. That is equal to your deposit, 25 grand, times 1 plus the rate, 0.0825, divided by 4, all raised to the 4 times t. We don't know the years, so we're going to leave that as your variable. So you're going to solve for t. So first of all, this parentheses, whatever these two things are being raised to an exponent. So you cannot times 25 grand to this. You cannot times these two together. That's going to jack you up. Because in your order of operations, first you do parentheses, so you can do this, and then you do exponents. And then after you do parentheses and exponents, then you times it. So move number 1. I'm going to undo that times 25 grand. I'm going to divide this side by 25 grand, and I'm going to divide this side by 25 grand. So you do 1 million. 1 million divided by 25 grand, and we get 40. Okay, now I'm going to change the parentheses. I'm going to do the parentheses and change that to a decimal. 1 plus 0.0825 divided by, divided by 4. Okay, so this is like 1.020625 to the 4t. Okay, now you got to undo the 4, and you got to undo the base. And the only way, you got to do the base first. The only way you're going to undo the base is to log. So now we're going to go log. This will be the base, 1.020625 of this, of 40, equals the exponent. Logs always equal the exponent. So now this is a calculator move. Do this on your calculator, and that's probably going to end up being some crappy decimal. That's okay. Don't round your decimals till the very end. So log in that base of 40. So I get like 180.6929 blah 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 equals 4t, and then ditch the 4. Divide that by 4. Divide that by 4. So if I divide that by 4, it actually says t equals 45.17. So look, that's actually pretty sweet. So you leave it in for 40 years and it grows to 655 grand. If you can leave it in for another 5 years, so pull it out at 45 years, it'll turn into $1 million. So at the very end, that's when it grows the very, very fastest. So every year you can leave it in beyond the 40 years, it's going to really grow. Okay, let's look at option 2. So how long are you going to have to leave your money in the bank for option 2 to pull out $1 million? So option 2 got us close. We pulled out 813 grand, so you only need like 200 more grand. So option 2, you want 1 million bucks. That is equal to your deposit, 25 grand, times E to the rate, 0.0825, times how long you're going to leave it in the bank, you don't know that. So that's our question. So again, do not times these two together, because first this you got to do exponents. You have to do this first. So move number one, ditch the 25 grand. So divide by 25 grand, divide that by 25 grand, and that was like 40. So now you got 40 equals e to the 0.0825 t. And the only way you're going to ditch the e is to do a log. So now we're going to go log base e of 40 equals 0.0825 t. Do this on your calculator, log base e of 40. And then divide it by 0.0825. So divide whatever that is by 0.0825. And it's almost the same, 44.7. So you gotta leave it in a little bit more to turn it into a million. 4 more years, 4 3/4 of a year. So almost not much of a difference between those two. Okay, now let's look at population growth. Population of the state of Oregon has grown from 3.4 million in 2000 to 3.7 million in 2006. Now they want us to use this formula. So y equals a times e k times t. So this is your answer. That is what you end with. A was what you start with. E is the number like pi. K is your rate. And T is years. So this formula kind of models exponential growth and exponential decay if k is negative. So if your rate is negative, then it's shrinking. So we're going to use this model right here for these next problems. So y is what you end up with, a is what you started with, k is the rate, t is time. So here we go. They want us to write an exponential growth equation following this form for Oregon. T is the number of years after 2000. So population grew from 3.4 to 3.7. So 3.7 is my y. That's what you end up with. So 3.7 equals a is what you started with, 3.4 times e. K, we don't know the rate at which that city's or the whole state's growing, so we're going to find that out. T, we do know that it took 6 years. Okay, so now we're going to solve for k. So just like we barely did in our compound interest formula, let's ditch the 6, let's ditch the e, let's ditch the 3.4. So first you have to ditch the 3.4. So you're going to divide by 3.4, divide this by 3.4, and that's some crappy decimal. So you got this, 3.7 divided by 3.4 equals e to the 6k. Now the only way you can undo the e is to log it. So it's going to be log in base e of this decimal, 3.7 divided by 3.4 equals 6k. And all you got to do for k is ditch the 6. Divide that by 6, divide that by 6. So k is going to equal 0.014. If we go 4 spots, k should be 0.0141. So that is here's your equation right here. But now we know k, so now we can find it for any year. So the population at any year is going to equal the starting 3.4 times E, and we know what K is. K is this is the rate of growth, 0.0141 times T. So this is the formula we're after. So if I want to know what the population is going to look like in 20 years, I just put 20 for T, do the math, and Y will be what it's going to end up with in 20 years. So this is the formula we want. So B, we're going to use that formula to predict what it's going to be in 2020. So that's just what I better said. So 20 years. So we started at 2000, so it is going to be 20 years later. So in place of T, we are going to put 20. So now on your calculator, you just type in 3.4 times E to the 0.0141 times 20, and that population is going to be 4.5076 million. Okay, question C. According to the equation, when is the population going to hit 6 million? So that's my ending, so that goes in place of Y. So it's going to be 6 equals 3.4 times E. The rate of growth is going to stay the same, 0.0141 times T. We don't know the time, so we're going to leave that variable. So we're going to solve for it. So ditch the 3.4, divide this by 3.4, divide this by 3.4, and here's what you got. 6 divided by 3.4 equals E to the 0.0141 T. And the only way you can ditch the E is to log. So now you gotta log it. You're gonna go log base E of 6 divided by 3.4 equals 0.0141 T. And now you just gotta get rid of the 0.0141. So divide this side by 0.0141. Divide this side by 0.0141. So log in base E of 6 divided by 3.4. And then divide that by 0.0141. And you get T equals 40.28 years. So it's going to take 40.25 years for them to go from 3.4 million to 6 million. Okay, now last question. I didn't type this in, I just barely snuck this one on, but I forgot all about it, but it's important, we gotta know it. So evaluate these logs with calculator, then express them in terms of common logs and evaluate with calculator, then express them in terms of natural logs and evaluate them again with the calculator. So calculator, do this on the calculator. Log base 6 of 12. So if you go log base 6 of 12, the calculator should give you 1.386852807. So crappy decimal. Now this is in base 6. So they want you in base, the common log. Okay, common log is base 10. And then they want natural log. Natural log is base E. Okay, so we're going to change it from base 6 to base 10, which is not too bad. So we're going to take the log in base 6 of 12, and we're going to change it to log in base 10. So we're going to take this part, that's going to be log in base 10 of 12, and make a fraction divided by log in base 10 of the old base. So 6 goes here. So punch this in on your calculator. Log base 10 of 12 divided by log base 10 of 6. Type it in, and you get 1.386852807. Same thing. And if you want to change it to the natural base, so that it's base E, so you're going to take that base 6 and we're going to go log base E of 12 divided by log base E of 6. And if you type that in on the calculator, you get the same decimal, 1.386852807. Okay, next one. Okay, so if you got log base 4 of 4, and we're going to do it on the calculator first. Log base 4 of 4, if you punch it in, you should get just 1. So no decimals, that's a nice one. Because it's really asking you, 4 is the base and 4 is the answer. What is the exponent? So 4 to the 1 equals 4. So it is 1. Because logs give you exponents. So the exponent's going to be 1. Now let's change it to common log. So let's go base 10. Then let's go natural log, base E. So we're going to take it and we're going to go log base 10 of this guy of 4 divided by log base 10 of the old base, which is 4. And this one's kind of easy to see, it's 1, because you got the same thing on top, same thing on bottom, so that's going to be 1. And now if you change it to the natural base, it's going to be log base E of 4 divided by log base E of the old base 4, and that is the same on top, same on bottom, so it is also 1.